This is a huge breakthrough. The James Webb Space Telescope has just unveiled the image of not one, not two, but 20 galaxies connected in a cosmic vine. And guess what? These galaxies date back to a time before the Big Bang itself. Can you imagine the mysteries hidden within these ancient formations? Are we on the brink of rewriting the cosmic history books? 13.8 billion years ago, an amazing event went down. The Big Bang. Yes, you know about it, of course. There's a major discussion about whether the Big Bang happened or not, but let's keep that highly flammable discussion on low fire for now. The massive explosion brought everything into existence. But what set off this megablast? What happened in those initial moments? And when did the first sparkly stars light up the cosmic stage? To find out, let's go back to the early universe during a blink-and-you'll-miss-it period known as the inflationary period, the birth of the universe. The conditions were extreme, densities and temperatures surpassing anything we encounter in our present-day universe. Scientists at the Center for Astrophysics at Harvard and the Smithsonian went to the most remote observing site on our planet, the South Pole. The lack of water vapor in the air makes it an ideal location to observe the cosmic microwave background, CMB, a faint glow of radiation that permeates the entire universe. Ever wondered how they study the birth of the universe in such a remote place? Here, they employ specialized instruments like BICEP 3, the Carey, and the South Pole Telescope, all designed to search for signatures of inflation in the CMB. Now let's talk about hydrogen, those abundant clouds emitting radio waves at a specific frequency. Astronomers use these signals to weigh galaxies and measure their motion through space. And then there's LIDA, working with a custom radio telescope to detect signals from hydrogen generated at the end of the cosmic dark age, less than 100 million years after the Big Bang. Can you imagine studying something so ancient, less than 1% of the age of the universe? The signal they're looking for is incredibly faint, but it promises to unveil the secrets of how the first large-scale structures, stars, and black holes formed. To complement LIDA's cosmic dark age research, scientists at the CFA Institute for Theory and Computation conduct simulations, exploring how the first stars came to be. Dark matter clumped together, attracting large clouds of hydrogen. When these clouds grew substantial, gravity stepped in, applying heat and pressure and igniting the first stars. Isn't it fascinating to imagine the birth of these celestial luminaries? Simulations suggest that these initial stars were colossal, hundreds of times larger than our sun. They burned through their fuel rapidly, ending their existence in a spectacular supernova, and sometimes leaving behind a black hole. Studying the early universe isn't just about satisfying our curiosity. It's about gaining meaningful insights into our own origins. The scientists at the Center for Astrophysics are at the forefront of this cosmic exploration. Now, let's fast forward a bit to a moment so infinitesimally small that it's hard to comprehend, the inflationary period. In a billionth of a trillionth of a trillionth of a second, the universe expanded by a factor of 10 to the power of 26. To put it in perspective, that's like a single bacterium ballooning to the size of the Milky Way. During inflation, quantum fluctuations at the subatomic level were projected onto cosmic scales, creating variations in matter density that laid the groundwork for the structure of the universe. As the universe expanded, the hot plasma of subatomic particles cooled, forming the first atoms, hydrogen. Light could finally travel freely, creating the cosmic microwave background, a faint glow that still permeates the universe. The CMB holds clues about inflation, offering a window into the earliest moments of our universe. The scientists at the Center for Astrophysics are on a mission to decode these clues, operating telescopes like BICEP 3 to observe the complex features of this ancient radiation. But while inflation is the leading theory, other ideas exist. Some propose that the Big Bang wasn't a singular event but a result of a bounce from the Big Crunch of the entire universe. The scientists at the Institute for Theory and Computation are working on new methods to decide which theory holds true. Now let's talk about the cosmic dark ages. After the universe cooled enough for atoms to form, the once scorching and bright cosmos turned cold and dark. Gravity played its role, amplifying tiny irregularities in gas distribution, forming voids and creating massive hydrogen clouds. As gravity worked its magic, clouds collapsed, giving birth to something new, stars. These early stars, scientists hypothesize, were different from the ones we see today. They were massive and short-lived, perhaps leaving behind black holes in abundance. Here's the challenge. Scientists have no direct observations of this era, leading to a literal and figurative dark age. To pierce through this cosmic mystery, the scientists at the Center for Astrophysics devised the Large Aperture Experiment to detect the dark ages. But imagine if everything we thought we knew about the birth of our universe was about to be turned upside down? Well, that's exactly what scientist Eric J. Lerner is suggesting in a recent study. He claims that the Big Bang Theory might not have happened at all. Could the origins of our universe be different from what we've been taught? Lerner, from the nuclear fusion research company LPP Fusion, challenges this narrative. He focuses on 3 critical fusion events believed to have occurred during the Big Bang, events that set the stage for the creation of helium, deuterium, and lithium. Drawing on decades of observations, Lerner argues that the amounts of helium and lithium in old stars don't align with the predictions of the Big Bang nucleosynthesis theory. According to this theory, a quarter of the universe's mass should be helium, but Lerner claims that old stars have less than half of the expected helium and less than 1/10 of the predicted lithium. Lerner boldly declares that no helium or lithium was created before the development of the first stars in our galaxy. Could it be that our understanding of the universe's early moments is based on flawed assumptions? Lerner suggests that challenges to the Big Bang theory, such as the closed universe and Hubble constant problems, as well as the lack of evidence for dark matter, have been dismissed by scientists. Is it time for us to reevaluate the very foundation of modern cosmology? In Lerner's eyes, the Big Bang theory faces a significant problem. The expected annihilation of matter and antimatter didn't happen, leaving behind a density of matter that contradicts extensive experiments. He argues that to avoid this outcome, the Big Bang theory requires an asymmetry of matter and antimatter, leading to consequences like the decay of the proton, which experimental evidence does not support. So, are we clinging to a theory that might be fundamentally flawed? Lerner doesn't stop there. He challenges another aspect of the Big Bang theory related to the expansion of galaxies. If the universe is expanding as the Big Bang posits, the surface brightness of distant galaxies should decline over time. However, Lerner claims that evidence supporting this effect has not surfaced. The heart of Lerner's alternative hypothesis lies in the galactic origin of light elements, or the GOL theory. According to GOL, the first generation of stars, 4 to 12 times the size of our Sun, produced helium, deuterium, and lithium by burning hydrogen at faster rates than our Sun. These stars dispersed these elements across the cosmos through stellar winds. Lerner argues that his observations of newly formed, more luminous galaxies align with the predictions of the GOL model far better than the Big Bang model. However, I couldn't help but consider the opposing view. Not everyone in the scientific community is ready to embrace Lerner's theory. Los Angeles-based astronomy and physics professor Vaya Perian points out that many of Lerner's arguments don't hold water. He emphasizes that the cosmic microwave background, evidence of radiation from the Big Bang, remains a pillar of cosmological theory. Perian raises a valid point. If Lerner's claims were robust, wouldn't we see more scientists questioning the Big Bang theory? Perian refers to astrophysicist Edward L. Wright's critique of Lerner's 1991 book, which Perian sees as part of a chorus of scientific voices debunking Lerner's theories. Wright, a former University of California, Los Angeles professor, refutes Lerner's claims about the non-existence of dark matter and the discrepancy in helium levels. Wright argues that stars releasing helium back into the interstellar medium also produce a significant amount of heavier elements. However, recent NASA findings support the existence of dark matter, a key point of contention between Lerner and his critics. Astronomers using NASA's Hubble Space Telescope confirmed a fundamental prediction of the cold dark matter theory, suggesting that all galaxies form and exist within clouds of dark matter. The scientific community seems divided on Lerner's claims, with some questioning the validity of his arguments and others finding merit in his alternative hypothesis. Well, the beauty of science lies in its ability to evolve, adapt, and embrace new ideas. As we think about the origins of our universe, Lerner's challenge to the Big Bang theory invites us to question, explore, and seek a deeper understanding. Are we witnessing a scientific revolution in the making, Or will the Big Bang Theory continue to stand the test of time? Only time, further research, and perhaps more bold challenges will reveal the answers to these cosmic mysteries. But that's not the only surprising news I have for you. Instead of a single explosive Big Bang that initiated the universe billions of years ago, scientists are now entertaining the idea of a second transformative event. A dark Big Bang that could hold the key to understanding dark matter. Dark matter, a mysterious form of matter, is thought to make up about 27% of the known universe, but it doesn't interact with light or electromagnetic fields in any discernible way. Astronomers have long grappled with the puzzle of why clusters of galaxies move in peculiar ways that defy the predictions of our current standard model of physics. The prevailing explanation suggests the existence of unseen matter, but despite our best efforts, this dark matter remains elusive. Now, what if there wasn't just one cosmic explosion at the beginning of time, but two? What if there was a dark Big Bang that occurred when the universe was less than a month old, giving rise to dark matter in a way we hadn't considered before? Catherine Free, a physics professor at the University of Texas at Austin, and her colleagues proposed this intriguing idea in a yet-to-be peer-reviewed paper. Free challenges the traditional narrative, suggesting that the universe might have undergone multiple phase transitions, gradually bringing everything from regular matter to dark matter into existence. It's a radical departure from the idea of a singular Big Bang. According to Free's hypothesis, this cosmic event might have taken place when the universe was less than a month old. Just imagine, within the first few weeks of existence, a transformative event that gave birth to a variety of dark matter particles, among them the intriguingly named darkzillas, colossal particles 10 trillion times the mass of a single proton. But what if the dark Big Bang wasn't a sudden burst, but rather a gradual, gentle emergence? In that case, it could have produced lighter dark matter particles referred to as dark cannibals. These particles, absorbing each other with each collision, share similarities with one of the leading dark matter candidates proposed by astronomers for decades: weakly interacting massive particles. Free is optimistic that studying gravitational waves, those ripples in spacetime, could provide crucial insights into her dark Big Bang theory. Instead of a singular explosive event, cosmologists are contemplating the possibility of multiple phase transitions shaping the universe over time. By measuring disturbances in signals from highly magnetized neutron stars called pulsars, scientists are attempting to trace the origin of gravitational waves. But this theory opens up a multitude of questions. Could there be more than one way the universe came into existence? What if our current understanding of the cosmos is just a small piece of a much larger puzzle? Free's work represents a frontier in cosmology, inviting us to question established theories and explore the mysteries that lie beyond our current comprehension. The idea of a dark Big Bang prompts us to consider the universe as a dynamic, evolving entity, undergoing various transitions that shape its structure and composition over time. But the question that has puzzled scientists for years is, how soon did stars and galaxies start forming after this colossal event? Now, thanks to the James Webb Space Telescope, we are getting closer to revealing the mysteries of the early universe. The James Webb Space Telescope was designed to pick up this shifted light, allowing astronomers to peer back in time and explore the early history of the cosmos. The initial data is promising, and astronomers are in a race to discover the most distant galaxies ever observed. Recently, a groundbreaking study focused on a set of distant galaxies, suggesting that one of them is larger than our own Milky Way, just 700 million years after the Big Bang. This finding challenges our understanding of the forces that shaped the universe. But how did scientists reach these conclusions, and what does it mean for our comprehension of the cosmos? Let's look at the methods astronomers used to study these early galaxies. The technique is rather simple but ingenious. The earliest stars and galaxies are surrounded by hydrogen atoms, which can absorb specific wavelengths of light in the UV range. This absorption leaves a distinct mark in the light emitted by these galaxies. Over the time it takes for this light to reach us, the universe expands, causing the characteristic signature to shift into the infrared part of the spectrum. Identifying this shift allows astronomers to determine the distance of the galaxy from Earth. In a recent study, a team of astronomers scoured a patch of the sky searching for galaxies exhibiting two specific features related to the ionization of hydrogen. This led them to a group of 13 galaxies with redshifts placing them between 500 million and 900 million years after the Big Bang. In other words, the light from the galaxies traveled for roughly 13 billion years to reach us. Knowing these galaxies exist is undoubtedly fascinating, but astronomers can go a step further by estimating certain properties of these galaxies. They can glean insights into the speed of galaxy formation and evolution. These estimates rely on the ratio of the intensity of hydrogen features to the light in the deeper infrared, which includes the starlight emitted by these galaxies. The research team used various methods to model the properties of these galaxies, running simulations with 5 different configurations. This comprehensive approach aimed to provide a range of values, recognizing that the actual values likely fall within this spectrum. Here's where things get intriguing. The brightest galaxy in this sample is unexpectedly massive. At the upper end of mass estimates, it surpasses 10 to the power of 11 times the mass of the Sun, making it larger than our own Milky Way. Yet, this massive galaxy appears only 700 million years after the Big Bang. Galaxies of this size at such distances have never been seen before. But how is it possible for a galaxy to grow so large in such a short time? Could it have companions that influenced its growth? The data suggests at least 2 nearby companions, hinting at a possible cluster formation. But if this galaxy is representative of others in the early universe, it challenges our current understanding. Most of the stars in the early universe, according to this data, were in massive galaxies. This goes against what we thought we knew about the distribution of galaxy sizes in the early cosmos. Now, let me pose a question to you. Is it conceivable that our current methods of estimating galaxy mass are flawed? What do you think? One possibility is that these methods were developed using examples that are more recent. When applied to more distant galaxies, they might not produce accurate results. The thing is, science is a journey of discovery, and sometimes the methods we employ need refinement. It's crucial to recognize that this study focused on a small area of the sky. It was chosen for examination because the Hubble telescope had previously imaged it. Are these massive galaxies a general feature of the early universe, or is this just a quirk of the observed region? To answer this, we need to look at additional areas where we already have data. The study of these early galaxies challenges our preconceptions about the formation and distribution of galaxies in the early universe. The unexpected size of the galaxies raises questions about our current understanding of dark matter, dark energy, and the available baryons necessary for star formation. Are we witnessing a fundamental shift in our understanding of the cosmos, or do we need to recalibrate our methods and assumptions? The cosmos may reveal even more surprises, pushing the boundaries of our knowledge and inviting us to think about the mysteries of the universe. However, I've got another mind-blowing piece of news fresh from the James Webb Space Telescope. A set of 20 galaxies just discovered that appear to be connected in a cosmic vine. These galaxies, located in an ancient part of the universe, could rewrite our understanding of cosmic formation.